Okay, so here's our 3.1.2 notes. You're going to be introduced to the idea of a tree diagram. So we did an area diagram last class, tree diagram this class. All right, so this is 3-12. So in 3-12, it's a lot like what we did on the previous slides. So I went through and I copied over all of the work that we did from our area model. But there's a little bit of a twist to this. So if we go through and take a look at this question, the idea is that being some sort of a competition between the two of us. So if the letters can form a 2-letter English word, you win. So otherwise your teacher wins. So we want to go through and we want to try to figure out which one of these would actually represent something of you winning. So, or words that could be made if we think about it that way. So if we do a U and a T, that's not a word. INT, yes, that definitely would be. So I think this box here with IT in it would be 1/8. AT is a word. UF is not. IF is, and AF is not. Okay, so the probability of actually getting a word out of this would be the sum of those three. So the 1/8, the 1/12, and the 3/8. So I went through and labeled out the words. So we have the probability that we would get the word it, which was 1/8, probability of the word if, which was 3/8, and the probability of the word at, which is 1/12. Remember, if these can be created, then you would win. So we've got the probability that you win would be, so I'm just going to go ahead and add all of those up because it was the word it or, remember or means add, or 3/8 or 1/12. So we would add all of those together and give us a 7/12. So I guess we could ask ourselves is this necessarily a fair game if we were to play this game? And no, it isn't. A fair game means that all players have an equally likely chance of winning or losing. So if this were to be a fair game, then the probability of you winning would be 6 out of 12 or 50% of the time. Okay, but what we want to do is use this as a jumping off point, be able to start thinking about a tree diagram. So it's another way to take a look at this type of information. So what I want to do is I want to start with the spinner number 1. And spinner number 1 has 3 things that could happen. So what we do is we have these kind of 3 little offshoots that we're going to do. And all of these offshoots represent the first thing that could happen, which would be spinner number 1. The first thing that would happen on spinner number 1 would be we could get a U, we could get an I, or we can get an A. And then what we do to try to organize this, because we still want the probability of each of these things on the spinner to be inside of our diagram, is we put that probability kind of down the branch of the tree. So the probability of U was 1/6. So what I would do is on that branch, I would put a 1/6. Then on the I, it was a half. And then on the A, the last probability was 1/3. So you just kind of keep them on the branches. So all of those things that we just did, the U, the I, and the A, this would all represent spinner number 1. So everything directly above that would be spinner number 1. Okay, but we're spinning spinner number 1, and then we're going to spin spinner number 2. So off of each one of these, so let's say you spun a U. All right, but you still have to spin the next spinner. So spinner number 2 had 2 things that could happen. So off of U, off of the result of your first spin, you now have the next 2 results. Now you could have spun either a T or an F. And we do the same thing, kind of go down the branches and we write down what the probability was. So T was 1/4, and then F is 3/4. So what we want to do is we want to build all of the branches, so build our tree. Now, let's say hypothetically that you spun an I. All right, well, then you're still going to spin a second time. And the possibilities for those were still T and F. The probabilities for those is still the 1/4 and the 3/4. Just go ahead and keep that going down the branches. And then we have the exact same thing happening with A. So A was the first spin, then you had your second spin, which could have been a T or an F. The 1/4 and the 3/4 hasn't changed. So now everything here represents spinner number 2. So now that we've built this, we want to be able to go down the branches to find the probabilities. If you think about this, our area models, we would have multiplied the probability of the first spin times the probability of the second spin. Well, we're still going to do the exact same thing. So what we do is we multiply down the branch itself. And I'm going to go ahead and color code the first one so you can see what I'm talking about. So we're going to start at the beginning. And let's say that we spun a U. So we would go down the branch of U first. So 1/6 is what we're going to get to. But then let's say our second spin was 1/4. In order to find the probability at the end of this branch, we're going to multiply the 1/6 times the 1/4. And that is going to give me 1 out of 24, which if you take a look back at the table, we also got, or inside the area model, we still got 1 out of 24. So when you're going through and figuring out the probabilities at the end of each of the branches, you're going to multiply down the branch all the way from the beginning. So if we do one more, and then I'll have you guys see if you can do the rest of them. So let's say we spun the U, and then we spun the F. Okay, so we would multiply down that branch. That's going to be 1/6 times 3/4. And then that would give me 3 over 24, but that simplifies to 1/8. You can also find that inside the area model. So go ahead and take a minute and see if you can fill in the results at the end of each branch. Okay, so now that we have all of the results, one of the things that you definitely want to keep in mind is that every single one of these results at the end, so we've got my black arrow pointing up, those would have represented the areas inside for each one of the rectangles. So this is the interior portion, the interior part of the area model. It's just another way to visualize the same type of thing. It's actually pretty nice too because the tree diagram allows you to go beyond 2 dimensions. So let's say we had 3 spinners. If we had 3 spinners, you could set up the first set of branches for spinner number 1. Then you would set up the second set of branches for spinner number 2, and then the third set of branches for spinner number 3. Now we're talking about 3 dimensions, which we could do, but I don't think it would be an area diagram anymore. It'd be a volume diagram. And then we'd have to draw a 3-dimensional cubic space to be able to use the other model for this. So what we have here is the idea of a tree diagram. It's just another way to represent some things. Again, it's nice because it allows you to do more than what the area model would do. So here we have an example. So go ahead and read this example to yourself, and then we'll go ahead and start playing around with this problem. Okay, so hopefully you have read this. We are now trying to get to, sorry about the typo, we're trying to get to room B. That's the goal. So the goal is room B. But I think we need to figure out, let's kind of play around with these different pathways. And I'll show you how I go through and address these problems myself. So let's say that we are the pet rat. Okay, so here we come walking the path. Here we come in. There is one pathway for us to choose from, and we've only got one way to go. So that represents, that single path right down the middle represents 100% probability of where we're going, assuming we're not turning around. Now, once we get to a juncture, we want to think about that these are different possibilities. So here, I have a juncture right here, and I see that I could go up or I could go down. There's 2 possibilities. So the probability that I would go up would be 1 out of 2, and the probability that I would go down would be 1 out of 2. So once I get to a juncture, I want to think about, well, how many different ways I could go. Okay, let's go on the upwards path. So if I go on the upward path, I see another juncture here. So I see this juncture happening, because otherwise I'm still down that same path I was before. But if you take a look, I now have 3 different ways that I could go. So out of the 3 possibilities, each one of these represents 1 path. So I think I have a 1/3 probability of following down those paths. And that's actually kind of nice, because it looks like one of them represents the way that I want to go to try to get to room B. All right, let's go back, because we need to take a look at the bottom path also. So the bottom path, every time, again, I get to a juncture. So whenever I have a choice, all right, it looks like I have a juncture right here. Well, I think there's only 2 paths, because I could either go up that way or I could go down this way. So that would be a 2. And so I've got an equally likely chance of going up the path or down the path, assuming I don't have any type of experience with this type of maze that I'm supposed to be going through. Okay, the top, it looks like I come to another juncture again though. So I could either go up or I could go down. All right, so that's 2. So a half this way and a half this way. If I take a look at the very bottom one, I don't think that I have another juncture, except for when I just get to room C, and it looks like I'm kind of stuck in there. So I do have a tree diagram. It's just set up a little bit differently. So now I want to think about, I'm trying to get to room B. So I'm going to highlight my paths here. So I could start here. I could go up and then down to get to room B. Okay, so I think that's one possibility. So that gives me, you guys know, as we go down the tree, we want to multiply. So I've got 1/1, because that was the only path I could take. Then the 1/2, which was blue. So this is my upwards path. And then I have, I think, another one. Yeah, I had a 1/3 option as well. So this is going to be the top path for me. So this is if we went to the top. When we multiply this, it looks like I'm going to get 1/6. Okay, let's figure out what the bottom path is. So the bottom path, I'll keep my color coding, so that was green. All right, let's see if we can do this one in purple. All right, so what I could do, start again. So start back where I was. This is my first option. Then I could go down. I'm trying to get to B. So it looks like I need to go up and then stay on the upwards course. All right, let's take a look at this. So I've got my 1/1 still. Times, okay, bottom path was half. Times, okay, then I went to the top juncture, which was the purple, and that was a half. Times, and then I had that other juncture as well. That was yellow, and that was my 1/2 as well. Okay, I think if I multiply all of those together, that's going to give me 1/8. All right, so basically, as the rat, the pet rat, we could either take the top approach to get to room B, or we could take the bottom approach to get to room B. So it is 1/6 or 1/8, so we're going to add these together. So what I would say is a probability that I'm going to get to room B is going to be 1/6 plus 1/8. And we go ahead and add those together, and that's going to give us 7 out of 24. And that covers the notes.